maximum kinetic energy the released electron's going to have is given by this equation. Now, let's just make sure we know what we're talking about. This EK in this equation is the kinetic energy of the emitted electron. The electron that flies off of the metal. This is its kinetic energy. And we would say that kinetic energy is equal to the energy of the incoming photon, which we said would have the formula h times f, Planck's constant, times the frequency of that incoming photon, minus whatever the work function is that would be, of course, specific to that metal. And here I'm focusing on potassium, mostly because potassium photo emits within the visible spectrum. All right, so the other ones that don't emit from the physical spectrum, like, require too much photon energy. You can't see the light shining on them. So potassium is kind of the one that people get excited about because you could shine light that humans could see in the late 1800s, and then that would make electricity flow. And in the late 1800s, that really mattered because you could see your experiment without having to rely on some instrumentation to quote unquote see invisible light. That makes sense to people, right? So that's why people classically talk about potassium as an exemplar of this. Anyway, let's put an equation off to the side here. We could say EK, we'll make this like a little bit tidier, more like math-like. EK for the electron equals h times the frequency of the incoming photon minus W, where W is the work function for that material. So I'll call it material specific work function. Now, I actually got to do this one better. This EK, which I'm going to shorten up to EKE, kinetic energy for an electron, is equal to H times F for the photon. I'm not going to change anything there, but I want to turn that W into an H times F naught. And people say, well, what is that? Well, that means that in order to get just up to the energy of the work function, right at the threshold, I would have to have a frequency of photons coming in to just barely approach the work function. They would have to be at the F naught value. So that's like the border. Any frequency higher than F naught is going to knock off electrons. But right at F naught, we call that the threshold frequency. And you definitely get this feeling that we've got like some overlap of physics and chemistry and, like neat ideas about quantum going on here simultaneously, right? So for every metal, there is a threshold frequency. And any radiation higher than that threshold frequency for incoming photons is going to knock off electrons. And we say HF naught is equal to the work function. So that gives the photon enough energy to produce a photoelectric emission. One time somebody complained that I was slow talking this too much. What I've also heard is that if I slow talk this and I tell a little story and I draw a little picture, it's just slow enough so that people can digest the ideas. Are you finding that the slowness is the right slowness for you? All right, so we're getting head nods on that. I don't want to go fast on this. I want to make sure it all makes sense. So if you have questions, just pause. Ask me to clarify something, okay? Because I want to tell this like it's a nice, clear story. I don't want to tell it like I'm trying to sell you an overpriced computer at Best Buy, okay? All right, so the number of photo emissions emerging from the metal, getting knocked off of the metal surface per unit of time is proportional to, now we're being repetitive. We've already said this earlier in the note, but we're saying it again with the hopes that you can digest it better the second time around and in words, okay? It's proportional to the number of photons. Remember, we picked up 2 flashlights instead of just 1, striking the surface. And that in turn depends on the intensity of the incident radiation. Okay, more flashlights, more photons. It follows that the photoelectric effect, or the photoelectric current, sorry, that's the flow rate of the electrons. Maybe I'll put that in little parentheses off the side here. The rate at which electrons are ejected from the metal. Man, we're turning a lot of short words into street language phrases. So the photoelectric current, the rate at which electrons are ejected from the metal, is proportional to the intensity of the radiation. So how bright, provided that the frequency of the radiation is above the threshold frequency. Now, that little 2-liner right there, if that 2-liner makes sense to you, then you probably digested the previous page of conversation. How many people feel like that 2-liner makes sense to them? All right, so some honest people keeping their hands down and some honest people putting their hands up. And if it doesn't make sense to you yet, give it a read through and ask me some questions afterwards. Absolutely, I'm happy to talk with you, okay? But the fact that some people put their hands up tells me that something clicked. But if things didn't click for everybody, don't give up on it, right? Like this definitely has a strong logic to it. Now, I wanted to take a little bit of a break here, and we want to move on to just talking about the hydrogen atom. So I'm going to stop recording, and then I'll start a new segment.